In this video, we're going to be looking at additional congruence properties. And we're going to talk about the angle side angle property, or the ASA property, and also congruence of quadrilaterals and other figures. Okay, we'll talk about the angle side angle property, or the ASA property. And it states this: if you have two angles and the included side of one triangle, and they're congruent to two angles, and the included side of another triangle, respectively, we can conclude that the triangles are congruent. So in this case, I have triangle ABC and triangle A prime, B prime, and C prime. All right, now let's look at this. Let's say if I want to show that angle A is congruent to angle A prime, and then angle B is congruent to angle B prime, and then let's say the included side. The included side has to be in between the two angles that I marked off here. So if I marked off angle A and angle B, the included side must be side AB. And the same thing here. If I marked off angle A prime and B prime, then side A prime, B prime must be the included side. Okay? So based on that particular case, if I can show that angle A is congruent to angle A prime, and angle B is congruent to angle B prime, and side AB is congruent to line segment A prime, B prime, then I can conclude that triangle ABC is congruent to triangle A prime, B prime, C prime, using the angle side angle property. Okay, the next one is the angle side property as well. If two angles and a side opposite one of the two angles of a triangle are congruent to two corresponding angles and the corresponding side of another triangle, then the two triangles are congruent. So in this illustration here, we have triangle ABC and triangle DEF. Or triangle EDF, I should say. Now look at angle A and angle E. They have a measure of 60 degrees, so angle A is congruent to angle E. Look at angle B and angle D. They both have a measure of 75 degrees, so angle B is congruent to angle D. And here, side AC is a side that's opposite angle B. So side AC is congruent to side EF. That's the corresponding side that's opposite angle D. So using the angle side property, we can conclude that triangle, let's say ABC, is congruent to triangle EDF. And notice how I named those triangles. So if I'm going to name one ABC, the other one has to be named the same way as the first, EDF. Okay, here's an example. Let's say I want to show that the triangles are congruent based on this particular figure that I have here. All right, now let's look at some things here. We got two 70-degree angles here. We can see that angle ABD, that's this angle right here, is congruent to angle BCD. I should say CBD. Because if I'm going to say ABD, I must say CBD. So I need to be consistent here. Also, take a look at this side right here. BD is the common side for both of these triangles. So I can say that BD is congruent to BD. Well, line segment BD is congruent to itself, line segment BD. And then I have another pair of angles that are equal to each other. This one. So if I'm going to say angle ADB, I must say angle CDB. They both have a measure of 50 degrees, so angle ADB is congruent to angle CDB. Well, the angle included side and the angle side angle. That property tells me that I can say triangle ABD is congruent to triangle CBD. So this is how we use the angle side angle property to show that a pair of triangles are congruent. Okay, here's another example. This time we want to show that the triangles are congruent. Okay, now this may be hard to see, but if you look at angle C, this is the common angle in, let's say, triangle ABC and triangle DEC. That's the common angle in both of these. So I can say that angle C is congruent to angle C. And then look at this angle, that's 30 degrees. This one is, okay, ignore this one. They're looking at ABC. That's this right angle right here. So ABC is congruent to angle DEC, because they're both right angles here. So angle ABC is congruent to angle DEC. And then they're using EC, line segment EC, to be congruent to line segment BC. So in this case here, if you are using the angle side theorem, then we can conclude that triangle ABC is congruent to triangle DEC. Okay, another example would be this. Using the definition of a parallelogram and the property that opposite sides in a parallelogram are congruent, prove that the diagonals of a parallelogram bisect each other. But now I'm going to walk you through this entire proof that they've written. What they want to show is that these diagonals, BO is congruent to DO, and AO is congruent to CO. Okay, that's to prove that the diagonals of a parallelogram bisect each other. Because if they bisect each other, then that means this piece and this piece are congruent, and then this piece and this piece must be congruent. Okay, let's start off with this. Line segment AD is congruent to line segment BCB because of the fact that opposite sides in a parallelogram are congruent, because you were given that. So here, AD is congruent to BC. We also know that AD is parallel to BC. Line segment AD is parallel to line segment BC because it is a parallelogram, because you have a pair of, you have two pairs of parallel sides. Since line segment AD is parallel to line segment BC, we can say that angle OAD, here's O, here's A, here's D, that's this angle here, and line segment angle OCB, here's O, C, and B, that's this angle up here. And then also on a similar note, angle ODA, that's this angle down here, is congruent to angle OBC. That's this angle up here. And the reason for that is this. If you have a pair of parallel lines that are cut by transversal, then we can conclude that alternate interior angles are going to be congruent. Okay, and from that we can use the angle side angle property. So in this case here, we have an angle, a side, and an angle, side, and an angle. we can prove that angle AOD is AOD right here, and triangle COB, that's this triangle up here, those are congruent to each other because of the angle side angle property. And then from that, we can say that line segment AO is congruent to CO, and line segment BO is congruent to DO because of the fact that corresponding parts of congruent triangles are congruent. Okay? And because of that, we can say that the diagonals do bisect each other in a parallelogram. Now let's look at some properties of quadrilaterals here. We'll start off with the trapezoid, which is a quadrilateral with at least one pair of parallel sides. So here, side BC is going to be parallel to AD. And one of the properties of a trapezoid is this: consecutive angles between parallel sides are supplementary. In other words, angle B and angle A, those are consecutive angles that are between the two parallel sides. They're supplementary. And anything that's supplementary means that the sum of these two angles must be 180 degrees. Also, angle C and angle D is another pair of consecutive angles. They too are going to be supplementary in a trapezoid. So in this case here, that measure of angle C and the measure of angle D must equal to 180 degrees. Next is an isosceles trapezoid, which is a trapezoid with a pair of congruent base angles. That means here's side AB and side CD. Those lengths are equal, meaning that line segment AB is congruent to line segment CD. And that means that these base angles, angle A and angle D, are congruent. Also, angle B and angle C are congruent. So those are your pair of congruent base angles. And of course, the properties here, each pair of base angles are congruent, and a pair of opposite sides are congruent. And if a trapezoid has congruent diagonals, it is isosceles. Next is a parallelogram, which is a quadrilateral in which each pair of opposite sides is parallel. In other words, here, side AC is parallel to side BD, and side AB is parallel to side CD. And those are the markings that we use for showing that one side is parallel to another side. And here's some properties for that. A parallelogram has all the properties of a trapezoid. What that means here is that the consecutive angles between parallel sides are supplementary. So it has that property. Also, your opposite sides are going to be congruent. In other words, side AB is congruent to side CD. Similarly, side AC is congruent to side BD. Opposite angles are congruent. Angle A will be congruent to angle D. Also, angle B will be congruent to angle C. The diagonals in a parallelogram bisect each other. So if I draw a diagonal AD and diagonal BC, of course those two diagonals bisect each other. And a quadrilateral in which the diagonals bisect each other is going to be a parallelogram. And then consecutive interior angles are always going to be supplementary. In other words, angle B and angle A are supplementary. They add up to 180. Angle A and angle C add up to 180 because there's consecutive interior angles. The sum of angle C and the measure of angle C and the measure of angle D will be 180. Also, the measure of angle D and the measure of angle B will be equal to 180 because those are consecutive interior angles. Okay, next is a rectangle. It is a parallelogram with a right angle. So in this case here, if angle A is a right angle in that parallelogram, then that means you have a rectangle. Okay, a rectangle does have all the properties of a parallelogram. And in a rectangle, all the angles of a rectangle are right angles. So angle A, angle B, angle C, and angle D are all right angles. And a quadrilateral in which all the angles are right angles would be considered to be a rectangle. Then the diagonals of a rectangle are congruent and bisect each other. So in this case here, the length of diagonal AC will have the same length as the diagonal BD. So those diagonals are going to be congruent, and they do bisect each other. So a quadrilateral in which the diagonals are congruent and bisect each other is a rectangle. All right, next is a kite. Now in the illustration they show you a convex kite that looks like this, and a concave kite that looks like this. Concave means that there's an indentation in that figure. And a kite is a quadrilateral with two adjacent sides congruent and the other two sides also congruent. So in this case here you can see that AD, line segment AD and line segment AB are congruent. Those two adjacent sides are congruent. Line segment DC and line segment BC is another pair of adjacent sides. They too are equal to each other. They're congruent as well. Lines containing the diagonals are perpendicular to each other. Okay, so if I draw a diagonal, in this case here AC, and the other diagonal BD, those two diagonals are perpendicular. They're going to form a right angle. So the lines containing the diagonals will be perpendicular. And also I can draw a diagonal with this concave kite. Here's the diagonal, and here's the other diagonal. Now if I extend this out a bit, you'll see that those diagonals are perpendicular to each other. And a line containing one diagonal is a bisector of the other diagonal. And one diagonal bisects non-consecutive angles. So in this case here, this diagonal is the bisector of angle C and angle A. This diagonal is the bisector of angle B and angle D. All right, next is a rhombus. RHOMBUS. Rhombus is a parallelogram with two adjacent sides congruent. In other words, line segment AB is congruent to line segment AD. Those are adjacent sides, they're both congruent. Also, side AD and side CD are adjacent sides, they too are congruent, and so on. So, a parallelogram with two adjacent sides that are congruent is considered to be a rhombus. And in a rhombus, it has all the properties of a parallelogram and a kite. And a rhombus is a quadrilateral in which all the sides are congruent. And then the diagonals of a rhombus are perpendicular to and bisect each other. Okay, so here, if I draw this diagonal BD and this diagonal AC, not only are BD perpendicular to AC, but those diagonals do bisect each other as well at a right angle. And each diagonal does bisect opposite angles. So this diagonal right here bisects angle B and angle D, and then this diagonal here bisects angle A and angle C. All right, next is a square, which is a rectangle with all the sides congruent. As you can see here, A, B, C, D. In this case here, AB, BC, CD, and AD are all congruent. So that makes it a square. And it does have the properties of a parallelogram, a rectangle, and a rhombus. Okay, next we'll look at this example here. Let's say I want to prove that a quadrilateral in which the diagonals are congruent and bisect each other is a rectangle. All right, if ABCD is a quadrilateral whose diagonals bisect each other, it is a parallelogram. So here we want to show that one of the angles in ABCD is a right angle. Okay, so let's look at angle BAD. That's this angle down here. Here's BAD. And angle CDA. Here's CDA. Those are supplements because ABCD is a parallelogram. That means that this angle measure and this angle measure add up to 180 degrees. Okay, now we can say that triangle ABD, that's this triangle down here, ABD, is congruent to triangle DCA. That's this triangle over here. And that's because of the side property. Since line segment AB is congruent to line segment CD, and that's the reason for the opposite sides of a parallelogram being congruent. AD is congruent to DA. Well, AD and AD, that's equal to each other. That's this side. And then you have BD congruent to CA. That was given to us. So we can say here that triangle BAD is congruent to triangle CDA. Reason for that is because of the corresponding parts of congruent triangles are congruent. And since these angles are supplementary and congruent, then that means that each must be a right angle. Okay, here's another example. Here in the figure, triangle ABC is a right triangle and line segment CD is a median to the hypotenuse AB. Prove that the median to the hypotenuse in a right triangle is half as long as the hypotenuse. Okay, let me explain what a median is. The median is always that line segment that starts from the vertex and it's always going to be going to the midpoint of the opposite side. So in this case here, line segment CD is the median. Starts at the vertex, which is C, and it goes to the midpoint of the opposite side. D is the midpoint of line segment AB, which means that D is in the center of AB. So CD is called, line segment CD is called your median. Okay, now we're given the angle C is a right angle, and D is the midpoint of AB. So what we need to prove that 2 times the length of CD is going to be equal to AB. And here's how we can do this. We're going to extend CD like this to attain CE, which is going to be 2 times the length of CD. So as you can see that CD has been extended to obtain CE. Then they connected the other 2 lines from A to E and then from B to E. All right, now D is going to be the midpoint of, well, D is given to you as the midpoint of line segment AB because it is the median. And it's also the midpoint of CE by that construction. Because of that, the diagonals of ACBE bisect each other, which means that ACBE is a parallelogram. And since angle C is a right angle, then by definition, ACBE is a rectangle. As the definition of a rectangle is a quadrilateral with at least one right angle. Okay, the diagonals of a rectangle are congruent, so CE is equal to AB. So here, CE is congruent to AB. That's one of the properties of a rectangle. The diagonals are congruent. So therefore, we can say that 2 times the length of CD is equal to AB. And then that means that the length of CD must be 1/2 the length of AB. Okay? And that's our proof. Okay. One way to determine if a quadrilateral is to give directions for drawing it. Start with the side and tell by what angle to turn at the end of each side to draw the next side, which is a turn. The turn is by an exterior angle. Thus, SAS seems to be a valid congruent condition for quadrilaterals. This condition can be proved by dividing a quadrilateral into triangles and using what we know about congruence of triangles. So usually these types of properties that we talked about, like the SAS and then the AS properties, and also the SSS properties that we talked about in the other video, can be used to determine some things about quadrilaterals. Okay, so that would conclude this particular video on the additional congruence properties.